This is the first video of Lesson 24, Section 4.2, talking about area and summation notation. Summation notation I will use interchangeably with sigma notation. Sigma is this large, it's a capital Greek letter here, this large operator here. That is what sigma is. This is how we write that. So here is an example of a sum. And in this example, the index of the summation is the little I that we see here. That also matches what the subscript is on the A inside of the summation. So our index of summation is I. The ith term of the sum, well, that is the expression that is inside of sigma. So the ith term of the sum is A sub I. The upper bound of this sum is n. Looking at the top, that is the upper bound of this sum. And the lower bound of this sum is 1. That is the number at the bottom that I starts off being equal to. So let's expand this sum and look at a few terms of it. Well, when I is equal to 1, at its lower bound, the very first I value, this would be A sub 1. And then I would move on to being equal to 2. So we would add A sub 2. And then when I is 3, we have A sub 3. All the way down, so I'm continuing in the same manner until the last term of this sum, and the last term happens when I is equal to n, and so that would be A sub n. So we start off letting I be the lower bound of the sum. We start with I being equal to 1, and then we end when I is equal to the upper bound of the sum, which in this case is n. So note that these numbers, the upper bound and the lower bound, they have to be constant in the problem. They cannot be changing. But the lower bound does not have to be 1. The lower bound can be any number as long as that number is smaller than the upper bound. So for example, I could have written the sum from I equal 3 to 5 of A sub I. Then this sum would start at A sub 3. Followed by A sub 4, and then the last term of it would be A sub 5. So it's not restricted that the lower bound has to be 1. It just can be any number as long as it is smaller than the upper bound. In this video, we're going to look at example 1, which has 5 different parts, where we're going to expand out these summations to get a better sense of what sigma notation is. So starting in the first example, example 1a, our lower limit is 1 and our upper limit is 4, and the ith term of our sum is I. And so we're going to have a term when I is equal to 1, and then we will add the next term that we get when I is equal to 2, and then we will add the third term that we get when I is equal to 3. And our final term will be when I is equal to 4. So starting with the first term, when I is equal to 1, well, the inside of the sum is just 1. When I is equal to 2, replacing I with 2, then we would just have 2. When I is equal to 3, we add 3. And when I is equal to 4, we add 4. And so this first sum is just 1 plus 2 plus 3 plus 4. And we know how to add numbers. I'm not terribly concerned with evaluating these summations in this example. I just want us to get a better sense of what sigma notation is. Later, we'll look at some formulas that we will use to evaluate summations. In example 1b, this time our lower limit is I is equal to 0. So the first term here will start when I is equal to 0. And then our second term will be when I is equal to 1, followed by when I is equal to 2. And then the final term will be at the upper limit when I is equal to 3. So let's plug into this sum to see what we get. When I is equal to 0, we have 0 plus 1 as our first term. When I is equal to 1, we have 1 plus 1 as our second term. plugging into this summation here. When I is equal to 2, I'm going to replace this I with a 2, so we will have 2 plus 1. And then finally, when I is equal to 3, replacing this I with 3, we have 3 plus 1. So let's simplify these terms here. The first term, 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. And then finally in the last term, 3 plus 1 is 4. So notice that in example 1a and 1b, the summations look different. They don't even have the same upper and lower bounds, but they're exactly the same thing. And so there are infinitely many different ways that you could write one summation by just playing with your indices and what you have as the ith term of your sum. Moving on to example 1c. We're going to start when k is equal to 3, so we will have 2 times 3 squared. When k is equal to 4, we will have 2 times 4 squared. When k is equal to 5, we will have 2 times 5 squared. When k is equal to 6, we'll have 2 times 6 squared. And we're going to go all the way up to when k is equal to 8. So our last term will be 2 times 8 squared. And so that is what example 1c looks like. In example 1d, we're going to work a little bit backwards here. Our goal here is to fill out the missing upper limit and the missing ith term of the sum. So you want to see what goes inside of that circle on top and that box for the ith term of the sum. We can see that the lower limit was given to us as j equal to 1. So we're looking at these terms here in this summation to see what's changing and what is staying the same. Well, what's staying the same is the 2 in the numerator, so we definitely have a fraction here as our ith term of the sum with a 2 in the numerator, and then we have a 3 multiplied by something, and that something is changing. In the first term it's 1, in the second term it's 2, in the third term it's 3, so on and so forth, all the way until we get down to the 15th term. And then what else is not changing is the plus 4 at the end of that. So essentially we just need to fill out this formula. So j is what we are multiplying the 3 by. It goes from 1 to 2 to 3, all the way up to 15, and then it stops. There's no more terms after the 15th term. And so the upper bound for our sum is 15. So when we start with the sum, and we're working backwards to fill out the summation, we're looking for what is staying the same in each one of the terms, and then whatever is changing, that must involve the index of the summation if it is changing. And then we'll look to see what is it in the very last term, and that will help us find the upper bound. Our last example, 1e, perhaps looks the scariest, but really is not. And this is, in fact, in this lesson, the form of a summation that we will be dealing with the most as we move on to approximate area. So when I is equal to 1, the very first term of this sum, I'm going to replace the I inside of the ith term with 1. We're going to have f of x sub 1, and then multiply that by delta x. Delta x is staying the same in each of these terms. I'll move on to when I is equal to 2. We'll have f of x sub 2. That will be multiplied by delta x. And then eventually I is equal to 3. So we have f of x sub 3 multiplied by delta x. And then I'll stop and I'll ... indicating that this goes on until it reaches the last term, which is when I is equal to n at the upper bound of this sum. And so the last term of our summation is f of x sub n multiplied by delta x. In this video, we are going to look at 2 properties of summations, and then we're going to discuss 4 different formulas that give us summation theorems, and all 6 of these together we will use to help us evaluate summations. So in the first one says that if we have the sum from I equal 1 to n of k is some constant, times a sum I, then we can essentially just pull k out in front of that summation. So when you notice, looking at the left-hand side of this, the only terms, or the only piece of the summation on the inside that involves the index, which is I, is the a sub I. There is no restriction on that k. The k has nothing to do with the index. So for example, if I have the sum from I equal 1 to, say, 3, and I want to sum up 2i, well, in this case, k is like my 2, and the I is my a sub I. We'll plug into this. When I is equal to 1, we would have 2 times 1. When I is equal to 2, we'd have 2 times 2. And then finally, when I is equal to 3, we would have 2 times 3. Now, noticing all three of these terms have a factor of 2 in them. And all of those 2's are coming from this 2 that was in our a sub I on the inside of that summation. And so we can pull this 2 out from all three of those terms, and that would leave us in parentheses with 1 plus 2 plus 3. So we have 2 multiplied with the sum from I equal 1 to 3 of just I, where we're just adding 1 plus 2 plus 3. So basically, we went from here to here by just factoring out the 2, pulling that 2 out in front. That is what the first property says. Looking at the second property now, it basically says that if you're summing a sum or a difference, you can break that up into 2 separate summations and either add them or subtract them. So say, for example, that we have the sum from I equals 1 to 3 of I squared minus 4i cubed. So I'm going to expand out some of the terms of this summation to see what we get there. So when I is equal to 1, we would have 1 squared minus 4 times 1 cubed. And then we would add, when I is equal to 2, we would have 2 squared minus 4 times 2 cubed. And then when I is equal to 3, we would have 3 squared, and then we would subtract 4 times 3 cubed. Now I'm just going to rearrange these terms so that I have all of the terms that are squared right next to each other. So I have 1 squared plus 2 squared plus 3 squared, and then I am going to rearrange my terms so that I have all of the 4i cubed terms with each other. So then we are subtracting 4 times 1 cubed, and we are also subtracting 4 times 2 cubed, and then we are subtracting 4 times 3 cubed. Now from the last 3 terms that I wrote, I could factor a negative out from all of those terms and write them as positive terms. So I have 4 times 1 cubed minus 4 times 2 cubed, plus, because we're factoring out that negative, and then plus 4 times 3 cubed. And I'll bring down those squared terms, 1 squared plus 2 squared plus 3 squared. So now I have 2 separate summations where I can write that first term as the sum from I is equal to 1 until 3 of just I squared. That's just that first term, the a sub I. And then we are subtracting, and we're subtracting, since this was a subtraction there in the middle, the summation from I equal to 1 until I is equal to 3 of 4i cubed. And so we were able to break this apart into the difference of 2 separate summations. So if we had a plus sign here in the middle to start with, we would have had a plus sign here, but because we had a subtraction sign, we have a subtraction sign there. So if this is plus, that is plus, and then vice versa. If that's minus, then that is also minus. So this property essentially says that we can break up a summation where the ith term of the summation is either a sum or a difference of two different terms. The last four boxes we're going to talk about in this video are our summation formula theorems. And these are four theorems that we will use when we are evaluating sums. And so say we have a sum with, say, 30 terms. Well, these formulas, depending on what we have on the inside of our summation, whether it's just a constant or whether it's just I raised to the first power or I to the second or I to the third power, these formulas will help us easily evaluate that summation. And we'll see some examples of using these formulas in conjunction with the properties above in our next example. In this video, we're going to look at two examples, example 2a and 2b, where we use the properties of summations and the summation formulas that we had in the previous theorem to evaluate these sums. So starting with example 2a, we have the sum from I equals 1 to 4 of I squared plus 3. The first thing I'm going to do is I'm going to use the second summation property, this one here, to write this as two separate summations because we have a sum on the inside of our sigma, and so I'm going to split this up into the sum from I is equal to 1 to 4 of I squared, and then I will add the sum from I equal to 1 to 4 of 3. So now, to evaluate this first sum, where we have I squared on the inside, we're going to be using the third summation formula theorem, because the third theorem tells us what to do when we have I squared on the inside. So we are going to plug into this formula, keeping in mind that our n is equal to 4. So applying that formula, we would have 4. That's our n, I'm plugging into this formula, times 4 plus 1. And then our third factor in the numerator would be 2 times 4 plus 1. And then we are dividing by 6. So what I just wrote here is coming from the third summation formula, since we are adding I squared on the inside of our sum, and our n is equal to 4. Then we will look at the second sum, where we have the sum from I equal 1 to 4 of 3. That looks like the first summation formula, because we just have a constant on the inside of our sigma. So now applying this formula, I'll make a note here that our C is equal to 3, and our n is still equal to 4. N is coming from the upper bound of the sigma, and our upper bound is 4. So then this sum would just be 3 times 4. That says to add 3 and to do it 4 times. So that is just 3 times 4. And now we will simplify what we have here. In the numerator of the first fraction, we have 4 times 5 times 9, and that is divided by 6, and then we are adding 12. And when we take 4 times 5 times 9 divided by 6, that is equal to 30. And 30 plus 12 gives us 42. And so that is our answer for example 2a. And now I'm going to go grab my graphing calculator and show you how you can verify this answer with the graphing calculator. It's important to also know how to write it out by hand, because if you were asked to evaluate this sum and the only thing you had was 42, and I can't see how you're using these formulas like this here, then that would not earn any credit. So make sure you also know how to use the formulas, and then I'll show you how to put it in the calculator so we can verify. So on my calculator, I'm going to hit math, and then you could go either up or down, but it's faster if you go up. I'm going to go up till I get to summation, where I see this sigma, and I'm going to hit enter on that. And you can see it gives us this blank sigma notation, where now all I need to do is fill this out. I need to put something for my index. I'm going to put X. It doesn't have to match. It doesn't have to be the I. I'm just going to put X there for my index. And then it starts off with the lower bound being 1. I will push up until I get to the upper bound, which I will make 4. And then inside of my sigma, inside of my sum, I'm going to put X squared, which represents the I squared. And then I will add 3. Now hit enter on that, and fantastic, we get 42, just like we computed by hand. Let's go ahead and plug 2b into the calculator, since we already have that pulled up, and then we will go through 2b by hand and show that we get the same answer that the calculator is going to give us. So following the same procedure, we're going to hit math and go up to summation. Hit enter on that. I'll let my index be 8. I'll let my index be X. My lower limit is 1. The upper limit of the summation is 8. And then on the inside here, I'm going to put another set of parentheses. And inside that set of parentheses, I'm going to put my X minus 2. And then I will square that. Do not square it on the outside set of parentheses. Don't square out there, because that's going to square the entire sum. So in other words, what I'm saying is don't do that. Don't put that 2 there. Put that square on the inside of that parentheses. So I'm going to delete what I just did and hit enter on that to see that we should be getting 92 for this whole sum. So now let's go and work this out by hand and verify that we in fact do get 92. So the first thing I'm going to do in 2b is I'm going to expand out the squared binomial that we have on the inside of the sum. I'm going to FOIL that out. I minus 2 squared, when it's expanded, is I squared minus 4I plus 4. And now that I have that expanded, I will use the second property to break this up into 3 separate summations. I have the sum of the first term, so from I equal 1 to 8 of I squared, minus the sum of the second term, I equal 1 to 8 of 4I, and then adding the sum of the third term, I equal 1 to 8 of 4. So we were able to break this up into 3 separate summations according to the 3 separate terms. And then before I start using the formulas to evaluate this, I'm going to use the first property. So the property that says that if we have a constant on the inside of our sum, that we can pull that constant out. And I'm going to use that property on the second summation that we have here, because we have this 4 in the front, and so I'm going to use that to pull that 4 out in front of that summation. And so now we have that 4 on the outside of the sum, which is exactly what we want, which just leaves us with I on the inside here in that second sum, and that's good because then we can use this second formula to evaluate that second sum. But let's start with the first one, where we have I squared on the inside of that sum. We're going to be using the third formula, since the third formula has the I squared on the inside, and I will make a note that our n is equal to 8. N is the upper limit of the sum. So I'm going to plug into that formula. So I would have 8 multiplied with 8 plus 1, and then multiplied by 2 times 8 plus 1, and that is all divided by 6. And then we will subtract, and we have that 4 out in front, so I'll put that 4, and then I will open some parentheses there. And we're going to use the formula from the second part of the theorem for that second summation, where we only have I on the inside of that summation. Using that formula, we would have 8 multiplied with 8 plus 1. I'm plugging n into the right-hand side of this equation, and then that is divided by 2. And then we will add what we have from that last summation. And this last summation we will evaluate using the first part of the theorem, since we just have a constant of 4 on the inside of that. So that theorem tells us that we should be taking our constant of 4 and multiplying it by our n value of 8. So we have plus 4 times 8. And now I'm just going to head back to the calculator. We have this whole expression here. I'm going to put this in the calculator and verify that it gives us the same answer that we got when we did it using the summation feature of the calculator. So now I have entered into the calculator exactly what we have filled out from our formulas and using the properties, and we are expecting that this gives us 92, same thing we got from when we calculated using the summation, and it does. And so we were able to verify that this summation is equal to 92. In this video, we're going to look at an example where we use rectangles to approximate the area bounded by some restrictions in the plane. So we want to use 4 rectangles of equal width to approximate the area bounded by the parabola 1 minus x squared, the x-axis, and the lines x equal to 0 and x equal to 1. And we're going to do 3 different methods. The first one, we're going to use right endpoints. So using right endpoints, that means that when we draw these rectangles in, we want these rectangles to have the right corner of the rectangle touching the parabola. So first, let's just talk about the boundaries that we were given. Clearly, we can see the parabola graphed, and I've intentionally cropped this picture so that we're staying in between the boundaries of 0 and 1. So x equal to 0, that is this vertical line here, that is the y-axis. X equal to 1, that is this vertical line here. The restriction of the parabola means stay under the parabola, so we will only be dealing with finding or trying to approximate this area here that I'm highlighting in yellow. And then the x-axis, well, we know that that is the x-axis, this line, this horizontal line here, where y is equal to 0. So if I want these 4 rectangles to have equal width, well then the length of, or rather the width of one rectangle would need to be 1/4. So the width of one rectangle is 1/4. And I'm getting that because I'm working over an interval of length 1 from 0 to 1. So I'm getting the length of that interval from subtracting 1 minus 0, my larger x bound minus my smaller x bound. And then I'm dividing by how many rectangles I want to have. So I want to split that width up equally. So the width of one rectangle is 1/4. I'm going to start drawing these rectangles in, keeping in mind that 1/4 is 0.25. And so now I am going to draw in my first rectangle. It has a width of 0.25, so it's going to stop there. And I want the right end point of this rectangle to touch the parabola. So I want that to touch the parabola right there. So our first rectangle looks like this. It has a width of 1/4. And the right end point of this rectangle is touching that parabola. That's what it means when we use right endpoints. Our second rectangle is going to start at 0.25 and extend until 0.5. So it's going to end right here. And I'm going to go straight up from 0.5 since that's the right end point of that rectangle. And I want that corner to be where this rectangle is touching the parabola. And so this is what our second rectangle looks like. For our third rectangle, it will run all the way to 0.75. So this is what that third rectangle will look like, going straight up from 0.75. I want the right endpoint of this rectangle to touch the parabola. So this is what our third rectangle looks like. And then finally, for our fourth rectangle, it has again a width of 0.25. And for the right endpoint to touch that parabola, well, that right endpoint is on 0. And so that rectangle does not have any height. So now we are going to add up the areas of these 4 different rectangles to approximate the area under this curve. So when I add up the area of a rectangle is base times height. So I'm going to write this as a summation. I'm going to start with I equal to 1, and I'm going to go up to 4 since we have 4 rectangles. So we'll be adding 4 different things. The height of all of these rectangles, I'm going to write as f of x sub I. F of x sub I. And the width of all of these rectangles is the same. That is, I'm going to call that delta x. So the f of x sub I, well, let's talk about what the x sub i's are. The x1, or x sub 1, that's the first right endpoint of our first rectangle. When we look at that first rectangle, the light blue one, the height of this first rectangle is the function value at 0.25. The height of that first rectangle is the function value at 0.25. So our f of x1 is going to be the function evaluated at 0.25. Remember, in all of these cases, delta x is 0.25. Delta x represents the width of the rectangle. So our first term in this summation is the function evaluated at 0.25, and then I will multiply that by the width of a rectangle, which is 0.25. And now let's go on to find the second term. Well, our x sub 2 is going to be 0.5 because the height of the second rectangle, of this green rectangle, its height is the function value at 0.5. At 0.5, that is where this function we shot straight up to grab that right endpoint. So the area of that second rectangle, we're going to have to take the function value at 0.5, and we're going to have to multiply it by 0.25. That's the width of all of our rectangles. Moving on to the third rectangle, the height of the third rectangle, we need to see where are we evaluating the function at? Well, we're evaluating the function at 0.75. That's where the third rectangle is touching the function. So our x3 is 0.75. So the height of that purple rectangle is the function evaluated at 0.75. And the width of that fourth rectangle, like all the others, is 0.25. And then finally, for our last rectangle, we need to look and see what is our x4, what is the fourth x value that we are evaluating the function at. Well, that is at 1. This right endpoint of this last triangle is hitting the parabola at 1. So our x sub 4 is equal to 1. So the height of that last rectangle, we can see in the picture that the height is 0. But technically speaking, the height is also the function value at 1, and the width of that rectangle is 0.25. And so now when we add this entire expression up, which comes from this summation, remember this was the last example that we looked at, something similar to this was the last example that we looked at in 1E. This will give us the sum of these 4 rectangles, which will approximate the area under this parabola. So to help us evaluate this, I have just gone ahead and put the function, our f or our y, into my y equals 1 minus x squared. And in the table, I'm going to evaluate this at 0, 0.25, 0.5, 0.75, and 1. Now, in this first part where we're doing right endpoints, we don't need the function evaluated at 0, but I just went ahead and did it anyways because we may need that eventually. and then I'm going to grab a clip of this table and pull that over so we can start simplifying this expression. So to make evaluating this a bit easier, I'm just going to pull a 0.25 out from this entire expression, since every term has a 0.25, and then that's going to leave us with this on the inside of the parentheses, and then we will add f of 0.5 and add f of 0.75, and then finally add f of 1. So continuing to evaluate this, we have 0.25 multiplied by f of 0.25. I'm just going to grab that from the table. That is the 0.9375. And then we add the function value at 0.5, which is 0.75. And then we add the function value at 0.75, which is 0.4375. And then finally, we will add the function value at 1, which we don't really have to do because that is just 0. And now I will evaluate this last line to get my approximation for the area using right endpoints. And all of this comes out to give me 0.53125. And so this is our approximation using right endpoints. Now, before we go on to look at the left endpoints, would we say that this approximation is more than the actual area or less than the actual area? Well, we can look at this sketch here of the graph and see that this is an under approximation, because there's a lot of area under here that this is not picking up. Everything I'm shading in red is not being captured in this process. And so we have a under approximation. The area under this curve is actually more than 0.53125. Let's see whether we get an under or an over approximation when we look at left endpoints. Now we are going to approximate this area using left endpoints. So when I draw my first rectangle, starting at 0, it still has a width of 0.25. I want the left endpoint of this rectangle to touch the graph. And so our first rectangle looks like this. The second rectangle will begin at 0.25, and I need to touch the graph on the left endpoint. So at 0.25, we're touching the graph now. Go horizontally across and then down. So this green area will represent the area of the second rectangle. The third rectangle touching the graph on the left side with a width of 0.25. This is what our third rectangle looks like. And then finally our fourth rectangle touching at 0.75, with a width of 0.25. This is what our fourth rectangle looks like. And so we need to add up the sum of our f of x of i's multiplied by delta x, which is still, of course, 0.25 in this example. This represents the height of the rectangle. That's what the f of x sub I represents, and the delta x represents the width of the rectangle, or the base of the rectangle. Here, our x1, our first x value we have is 0. That is the left endpoint that this graph is touching, that this rectangle is touching the graph on. The second x value, x2, in our second green rectangle, we use the x value of 0.25. In our third rectangle, the x value that we are touching the function at is 0.5. And then finally, in our last rectangle, the x value that we are touching the function at is 0.75. And so now we are ready to evaluate the function at these 4 values and to add up our sum. So we will have f evaluated at 0 multiplied by 0.25, that's our delta x, and then we will evaluate the function at our second x value, which is 0.25, and then multiply that by our delta x, which is again 0.25. Then we will add the height of the third rectangle, which is the function evaluated at 0.5, and multiply that by the width of the third rectangle. And then finally, we will add the function evaluated at our fourth x value, which is 0.75, and then multiply that by the width of the fourth rectangle, which is 0.25. I'm going to factor the 0.25 out from all four of these terms. So this is what we are left with in parentheses, and we will use the same table from earlier. So now you can see why I plugged 0 into this function. F of 0 is 1, and then we will add f of 0.25, which is 0.9375, and then we will add the function evaluated at 0.5, which gives us 0.75, and then the last term we have to add is the function value at 0.75, which is 0.4375. And then I will put this into my calculator and see what approximation this gives me for the area. And the left endpoint approximation is giving me 0.78125. Now again, we can look at this picture and say this is an overestimation, similar to how in the last example we said that was an underestimation. This is an overestimation because this is picking up pieces. Some of these rectangles are grabbing pieces that are not under that curve. So all this area that now I'm shading in red, we really should not be counting it because that's not area under the curve. So the right endpoints gave us an underestimation. It didn't grab enough area. And now the left endpoints are giving us an overestimation. I can't say that that's always the case. I could come up with a function where the right endpoints would be the overestimation and the left endpoints would be the underestimation. It just depends on what that function looks like, particularly whether it's increasing or decreasing on the interval that you're looking at. In the last part of this example, we are going to not use left or right, but midpoints to make our rectangle. And then we're going to look at all three of the estimates that we have from the right endpoints, from the left endpoints, and then from the midpoints, and use those to bound our area. So using midpoints, our rectangles are still going to have the same width. Our rectangles are still going to have the width of 0.25. So our first rectangle is still going to run from 0 to 0.25, but midpoints mean that I want this rectangle not to hit on the left, not to hit on the right, but to hit in the middle of the function. So I want the rectangle to hit right there. And so to figure out what that x value is, which is how we're getting the height of this first rectangle, depending on where this rectangle is hitting the function, I'm going to take 0.25 and I'm going to divide it by 2. So my x1, the very first x value that I'm using to get the height of the rectangle, is going to be 0.25 divided by 2, which equals 0.125. Now, moving on to my second rectangle, it is still going to have a width of 0.25, but now I want this rectangle to hit in the middle of that interval, so halfway between 0.25 and 0.5, and so we need to calculate what that x value is, so then we can plug it into the function and get the height of this green rectangle. So for our x2, we already know that half of the distance between 0.25 and 0.5 is 0.125. That's half of 0.25. So when I go half of that, I'm starting at 0.25, and then I am adding 0.125 to give me my second x value of 0.375. So I computed that by starting at 0.25 and then adding half of that distance. So I stopped right there where that green arrow stopped at. And half of that distance is half of 0.25, which we calculated for x1, which is 0.125. So now looking for our x3 value, we know that our third rectangle will still have a width of 0.25, but it will hit the parabola, hit the graph in the middle of 0.5 and 0.75. So this is what that third rectangle looks like. And to calculate what x value is in the middle of those two, there's two options. We could either take 0.5 and we could add 0.125 to it, or in reality we could just average these two x values. So I could take 0.5 and add it to 0.75 and then divide it by 2, and that's going to give me 0.625. Notice that if I would have taken the first x value of this triangle, which is 0.5, and added half the width of this triangle, which is 0.125, we would have gotten the same thing. So either way, you can either average the two endpoints of the rectangle, or you can take the left endpoint and add half the width of the rectangle. Finally, for our last rectangle, we'll find our x4 from that. It still has a width of 0.25. It stops at 1. Hits that parabola in the middle of that interval. And so to calculate the middle of that interval, I'll again take the average of these two x values. So averaging 0.75, which is the endpoint on the left of that rectangle, and 1, which is the endpoint on the right of that rectangle, gives us 0.875. Which I'll make a note of is again the same thing as taking 0.75 and adding half the width of that rectangle, which is 0.125. So now that we have all of our x values, we are ready to compute our sum. We will be adding up the heights of our rectangles, which will come from plugging our x1, x2, x3, x4 into our function. And then we will multiply by our delta x, which is still 0.25. So I'm going to go over to the calculator and I'm going to keep my y equals the same. My y equals will be this parabola, but I'm now going to plug in these 4 x values to get the function values, and then I'll bring a clip of that table over here so we can use it to fill out this summation. So I have evaluated the function at our 4 different x values. So now I'm ready to look at what my sum is. When I plug my first x value of 0.125 into the function, we end up with a height of that rectangle being 0.98438, and we're multiplying that by 0.25. And then we will add the height of the second rectangle, which is the function evaluated at 0.375, and that height came out to be 0.85938, and we'll multiply that by 0.25. And then we will add to that the height of the third rectangle, which is the function evaluated at 0.625, and that height is 0.60938, multiplied by the width of that rectangle. All these rectangles have width 0.25. That's never going to change in these problems. The width is going to be consistent as long as you're always working with the same number of rectangles. The height of our last rectangle is the function evaluated at 0.875, which is 0.23438. And I will multiply that by the width of the fourth rectangle, which is 0.25. And then I will evaluate this entire sum to get that the midpoint approximation of these rectangles is 0.671875. And if you're not getting this exact value, this is the exact value of the sum of the area of these rectangles, your calculator is probably giving you 0.67 0.188. You have to remember that these values here, those are rounded. And so because those are rounded, this answer is coming out a little bit rounded. But either one of these answers I would accept as full credit. I understand that the calculator rounds the heights of these rectangles, and so by default your answer is going to come out a little bit rounded. The only way, or one way that you could get the exact value is, say for instance, instead of using this approximation for the height of the rectangle at 0.125, you could actually plug 0.125 into this parabola. And so the equation of our parabola was y is equal to 1 minus x squared. Well, if we actually evaluate the function at 0.125, we'd have this. So if you use this expression instead of this rounded expression that the calculator gives you, then you would get the exact values. But again, either one is correct and earns full credit. So for the last part of this video, let's talk about bounding the area. We did a lot of work to get 3 different approximations. And let's just look 1 second at this midpoint one. The midpoint one has a little bit of overcounting happening here in red, where we're taking some area that is not under the curve, but then it also has a little bit of undercounting happening in these spots that I'm now shading in orange, where it's not grabbing all of that area. So the midpoint takes a little bit more, but then it looks like it's almost canceling that area out. And there's a little sliver in here we can't really see that's not being counted. And so we have 3 different approximations. Let's go and look at them. The first approximation we had was 0.53125 from the right endpoints. Then the left endpoints gave us 0.78125 for the area. And then the midpoint approximation gives us 0.67188 for the area. It's always going to happen that your midpoint approximation is going to fall in between your right and your left. Remember, I can't say for sure that the right is always smaller or that the left is always bigger. Those two could change whether they're smaller or larger, but the midpoint should always be falling in the middle. And so bounding this area from our 3 approximations, we can't say exactly what the area is, but we can definitely say that it is in between 0.53125, that's the smallest approximation that we got, and 0.78125, that's the largest approximation that we got. And we can see that this midpoint approximation does fall into that interval. So we're able to bound the area from our largest and our smallest approximations using rectangles. So we are building up to talk about how we can find the exact area of a region in the plane instead of just approximations for it using rectangles. And so I have 3 different I'm going to have 3 different scenarios here, and we're looking for which of these scenarios is going to give us the best approximation of the area bounded by sine 2x, x equal to 0, which is the y-axis, x equal to pi over 2, and the x-axis. So all 3 of these graphs here are the same graph. It's sine 2x, and I'm making sure that we're on the interval we want to be on from 0 to 2 pi. And so in all 3 of these cases, we're talking about the region that is above the x-axis, to the left of pi over 2, and to the right of the y-axis and under that curve. So let's let our n value vary. So let's say that in the first example, I just want n equal to 2. N represents the number of rectangles. Let's say I just want n equal to 2, and I'll use midpoints on all of these approximations, say. It doesn't matter, I could use left, right, or midpoints. I'm just using midpoints to make my point here. So in my first rectangle, it would stop at pi over 4. If I'm going through midpoints, this is the first rectangle. The second rectangle going through midpoints would have the exact same height due to some symmetry we have going on here. and there would be that one there. Let's look and see what's being counted that shouldn't be counted. I'm going to shade that in red. I shouldn't be taking all this area there, and we really should not be taking all this area here, since that's not under the curve. Now let's say in the that I want 5 rectangles. Let's say 4 rectangles. Let's say I want n to be equal to 4. I'm still going to do midpoints. So about midway here, I'm just rough sketching this. This would be my first rectangle. My second rectangle would be about right there. My third rectangle would be about right there. Looks like those two have the same height, again due to some symmetry happening in here. And then my last rectangle about midway, say that's about right there. That would be like that. I'm going to shade in red the regions that are being counted that shouldn't be counted. That's outside of it. This is outside. That's above the curve. By outside, I mean it's above the curve. It's not falling where it should. And then I'll go and I'll shade in, let's use yellow. What's not being counted but should be counted. So this isn't a perfect estimate either. We have a bit of overcounting and a bit of undercounting. So in the third scenario, let's say that I want n to be equal to 16. So I'm going to try to squeeze 16 rectangles into under that curve. Now notice that this is split up into, by these grid lines, we have 4 separate little sections. So I'm going to squeeze 4 rectangles into each one of those sections. So just to show you how I'm going to do the first piece, I'm going to draw 3 lines in here, because if I want 4 sections, I need 3 lines. And then on each one of these, I'm going to approximate the middle of that rectangle and make a little sketch for what that looks like. And then I'll go and I'll do that for the other 3 remaining pieces as well. So I know this is kind of rough, but as you all know, I'm a master artist. So here is my 16 rectangles in here. I'm gonna come through here and look at what should not be counted. There's a few little tiny corners in here. It doesn't really seem like there's a lot of space that I even really can grab in here of what should not be counted. And then we have a little bit that I'll hit in yellow that we can see that we're counting, that we're not counting that should be counted. So like some spaces in here where it's not covered by a rectangle. Some tiny little spots in there. I'll put some tiny little dots in there. Okay. So I think the point has been made. From these 3, which of these would you say has the least amount of space that is counted or overcounted? So we're looking at the red and the yellow. And by the way, I'm looking at that first picture now. There's a huge chunk at the top of that I need to shade in yellow because we're not grabbing any of this area when we really should be. So looking at these 3 scenarios, looking for the McDonald's colors, red and yellow, I think it's really clear that this last one with the 16 rectangles is doing the best job of approximating the area under that curve that stays in between 0 and pi over 2. And so the idea behind this is the more rectangles you have, the better approximation. The more rectangles, the better. So with that in mind, that the more rectangles we have, the better approximation we'll have, well, how can we take that concept and use it to find the exact area under a curve? Well, it would be nice if we could put infinitely many rectangles under the curve, but we see how much of a struggle it was for me to draw 16 rectangles. I definitely can't draw infinity. I mean, that's not even possible. I'd be here forever. But with calculus, we can take the limit as the number of rectangles approaches infinity. So that takes us down here to the limit definition of area of a region in the plane. If we have a continuous function that is non-negative on some interval, so notice all the examples we've dealt with, we're working all with the function on intervals where the function is above the x-axis. The area of the region bounded by the graph, not an approximation, but the actual area of the region, bounded by the graph, the x-axis, and two vertical lines, just like the examples that we've had, is equal to the limit as n approaches infinity of the sum from 1 to n of f of ci multiplied with delta x. So same general concept that we were doing in our example when we went through right endpoints, left endpoints, and midpoints. This expression in here is going to take that's calculating the area of the rectangle. And so the idea here is that if we could have infinitely many rectangles and take all of their areas and add them up, we would have the exact area under the curve. One thing I do want to talk about before we look at an example of using this is this CI in here. That is any x value that is in the ith rectangle. So what that means is it doesn't necessarily have to be the right endpoint, it doesn't necessarily have to be the left endpoint or the midpoint. It could be any x value that falls into that rectangle. So just for a quick example of that, look at this first rectangle here in this first n equal 2 example. My CI could be this x value right there. It could be this x value right here. Any x value as long as it is in that rectangle. In this video, we're going to look at example 4 from lesson 18. We did look at, I think one of the first examples that we looked at in lesson 18 together was an example of using this limit definition to find the area under a curve. But let's also look at this one here. So I have pulled up from Desmos the region that we're interested in. I have the graph of x squared minus x cubed in red, and then in blue we have the line x is equal to -1, and in green we have the line x is equal to 1. So we can see that the region that we're finding the area of is this region right here, because it's also bounded by the x-axis. And we're going to be finding that area using this limit definition. So first, let's just recap what's going on in here. Essentially, what we're doing is we are putting infinitely many rectangles under this curve, and we are finding the area of all of these rectangles, and we are adding them up. So I'm not going to draw in all these rectangles, but that gives us an idea of what we're doing there. So according to the formula we have circled above, the area is equal to the limit as n approaches infinity of the sum of f of ci times delta x. Let's start with, and this sum goes from 1 to n. Let's start with f of ci. F of ci represents the height of the ith rectangle. So let's just say that I'm talking about this rectangle right here. If I wanted to find the height of that rectangle, I would need to know what this CI, what that x value is, and then we would plug that x value into the function to see just how high it is actually going. Well, to find that x value, we have to remember that this started at -1, and it moved over however many rectangles, it moved over I rectangles, because that is the ith rectangle. So if it's moving over I rectangles to -1, we have to add I multiplied by 2 over n. Now let's talk about where the 2 over n is coming from. The 2 over n is coming from the width of one rectangle, which is what delta x represents. And the width of one rectangle is going to be the width of your entire interval. Our interval is from -1 to 1, and so that has a width of 2. And you get that by doing the larger number, subtract the smaller number, so that's 1 minus -1. And you divide by n, because we have n rectangles. And this is giving us 2 over n. So if I know that the width of one rectangle is 2 over n, that's where this 2 over n right here is coming from. Because remember, we started... You can't really see this -1 because the line is covering it, but we started at -1, and then we moved over I different rectangles. The I is represented right there, and to account for how wide each rectangle is, we're multiplying by 2 over n. So now we have, I'm going to go ahead and plug all this into our area formula. the limit as n approaches infinity of the sum from I equals 1 to n of f of ci. We already now know is going to be f of negative 1 plus 2I over n. That's this being plugged into the function f, and then all that's going to be multiplied by delta x, and delta x is 2 over n. So I'm going to write out what this is before I actually simplify it. The f of ci, we need to plug the negative 1 plus 2I over n into the function. So we would have negative 1 plus 2I over n squared minus negative 1 plus 2I over n cubed. And then all of that would be multiplied by 2 over n. Now I've already simplified, I'm missing my limit. I've already simplified everything that's in purple, so I'm going to go ahead and fill out what that is. And everything that is in purple is negative 8I cubed over n cubed plus 16I squared over n squared minus 10I over n plus 2. And all that is still multiplied by 2 over n. And now I'm going to go ahead and distribute that 2 over n in. So distributing the 2 over n, we have a negative 16I cubed over n to the 4th. So we're doing this. That will give us a 32I squared over n squared. This will give us a negative 20I over, no, this should be over n cubed. This will be over n squared. And then this will give us a 4 over n. And now I'm actually going to start breaking this apart into different summations. This is the limit as n approaches infinity of. So inside of our first sum, we have the sum from I equals 1 of negative 16I cubed over n to the 4th. This is I is 1 to n. And then there's another sum. And I think after seeing this example and the example that we did in class, and then especially after you finish looking at the examples on your classwork, because I've already had some conversations with some of you about how this works, you'll see that you don't necessarily have to write it out like this every single time, but I want you to understand what's happening here. So I've broken this up into the 4 separate sums, and now I'm going to go to each sum and I'm going to pull out any constants. Because remember, the index of this sum, the index of all of these sums is I. So the only thing that needs to stay on the inside of the sum is anything that has an I in it. Anything that does not have an I is considered a constant for that sum. So for example, in the first sum, we can pull out the negative 16 from the top and the n to the 4th from the bottom, which leaves us with the sum from I is 1 to n of I cubed. In the second sum, I'm going to pull out the 32 over n cubed. Next, I'm going to pull out the 20 over n squared. That's just going to leave us with I on the inside. And in the last sum, I'm not going to pull anything out just because there would be nothing on the inside. But the point is that in this sum, there's nothing here with an I in it. And so everything in there is considered a constant. So we're just adding that up n times. So if you have your the formulas from earlier, which we're going to be using these in a second, that's dealing with something like this. Because what's on the inside of the sum, in fact, let me drag this down here. Because what's on the inside of the sum does not have an index of I in it at all. And so to evaluate that last sum, we just take whatever is on the inside, which in this case was 4 over n, and we multiply it by however many times we're adding it up, which is n times. So that gets multiplied by n there. And notice that now, after we have pulled out everything that wasn't a constant, The only thing we're left with on the inside of our sums is exactly what we have in our summation formulas theorem. So this sum has just an I cubed on the inside, which is exactly the number 4 in the theorem. This one has just an I squared on the inside, and that is exactly number 3 in the theorem. This one has just an I on the inside, and that is exactly number 2 in the theorem. And so now we're ready to go and plug all those in so that we can do some evaluating. So we have the limit as n approaches infinity of -16 over n to the 4th. And that first blue box, the sum of I cubed, is equal to n squared times n plus 1 squared all over 4. And I'm getting that from number 4 in the theorem. And then we're adding 32 over n cubed, and that's multiplied by the sum of I squared, which is n times n plus 1 times 2n plus 1 all over 6. And then we have a -20 over n squared. That's multiplied by the sum of I, which is n times n plus 1 all over 2. And then at the end, we're still adding 4. And now we're actually going to go in and apply the limit out in the front. Now, when we're applying the limit out in the front, you have to think back to when we learned about limits. If the degree of the top matches the degree of the bottom, then we just take the ratio of the leading coefficients. And that's what's happening in all of these terms here, at least the first 3 terms. In the first term, the degree of the bottom is 4, and the degree of the top is also 4. So the n to the 4th over the n to the 4th tells us that when we take this limit, all we really need to be looking at is the -16 in the top and the 4 in the bottom. Same thing with the second term. The degree of the bottom is 3, and the degree of the top is also 3, because you have an n, and another n. So when we take the limit of the second term, we need to look at the 32 that's in the top, this 2 that's in the top of that n, and this 6 that's in the bottom. So we have 32 times 2 over 6. In our third term, the degrees match again. The bottom has degree 2, the top has degree 2, because there's 2 n's being multiplied there. So we're really only concerned with the -20 in the top and the 2 in the bottom. And then we have that plus 4 in our last term. So this is a -4 that cancels with that +4, and we're just left with 32 times 2 over 6 minus 10, which gives us 2/3. And that's our answer. And we could check that in our calculator by looking at, what is this, x squared minus x cubed? Yeah, this integral in our calculator. And that will also give us 2/3.